Hi everyone, welcome. I'm Devasattam and you're watching the 8th lecture of EE635 Applied Linear Algebra. This happens to be the first module. So in this lecture, we are going to look at, so we have already started looking at linear transformations between vector spaces over the same field. In this lecture, we're going to look at the so-called matrix representation of linear transformations or linear maps. Okay, we'll see how these linear maps can actually be always represented by a matrix, provided it's a map from a finite dimensional vector space to a finite dimensional vector space. Okay, so without further ado, let us start with our discussion. I need my screen, which should be, yeah, there we are. Okay, so as I said, we're going to talk about matrix representation of linear transformations. So let me just recall quickly what linear transformations are. So as you know, if V is a vector space and W is another vector space, both of them are over the same field. F, all right? Phi is a mapping from V to W. It would be called a linear map if it satisfies the property that phi of alpha V1 plus V2 is equal to alpha phi V1 plus phi V2 for all alpha in the field and all V1, V2 in the vector space V. Yeah, of course, V is called the domain of this linear map and W is called the codomain of the linear map. We've also seen two subspaces associated with every linear map, namely kernel of phi, which is a subspace of V, and image of phi, which is a subspace of W, right? Now, this lecture is dedicated to the fact that, dedicated to understanding the fact that such linear maps, if they are such that this, the domain V as well as the codomain W, both of them are finite dimensional, then it is possible to represent this map through a matrix. Okay. Now, why matrix? Okay. The answer to this question of question that why matrices would become obvious. I mean, the first step towards understanding this question would be the fact that matrices are the quintessential objects that uh, that symbolizes, yeah, linear maps from vector spaces which are given by tuples of numbers. Let me demystify this very long and complicated sentence. What I mean is, so let us first try and look at linear maps between those vector spaces which are not those abstract vector spaces, but the manifest vector spaces that we understand much more clearly, namely f to the power n, f to the power m, and I want a linear map from here to here. How does this linear map behave, or how does this linear map really look like? So elements here we know are the ones of the form alpha 1, alpha 2, dot, 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 alpha n. It's an n tuple. Similarly, elements here are m tuples, namely beta 1, beta 2, dot, 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 up to beta m. So these are the vectors that are there in f to the n and f to the m, right? Okay. Now, suppose we know that phi is linear. All right. What more can we say about this phi? How does this phi really look like? We'll see that just this information that this is a linear map will tell us that phi is nothing but a matrix, where the linear map phi is given by, take that matrix, multiply this matrix from the left to this column vector alpha 1 up to alpha n. That will give you the effect of the linear map phi acting on this vector alpha 1 up to alpha n. Yeah, why? Let's see. So once again, So if I have phi, okay, notice that this f to the n has a basis, the standard basis given by E1, E2, dot, 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 up to En, right? What is E1? E1 is this vector, this basis vector. E2 is this basis vector. En is this basis vector, okay? Now, if these are basis vectors, clearly phi when acts on E1 would produce something. What will it produce? Of course, this is an element in f to the m. So obviously, phi E1 must be some m tuple. Suppose we call that m tuple as A11, A21, dot, 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 up to AM1, right? Similarly, suppose phi acting on E2 would be A12, A22, so on up to AM2. Okay, we can continue doing this till we get phi of E1, so En, which is A1n, A2n, dot, 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 up to AMN. Okay, now consider this arbitrary vector, say V in f to the n, where this V is this n tuple given by alpha 1, alpha 2, dot, 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 up to alpha n, isn't it? Now clearly the way we have written these basis vectors, this means this is nothing but alpha 1 into E1 plus alpha 2 into E2 plus dot, 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 up to alpha n into En. So when my linear map phi acts on this V, by linearity what we get, by linearity of the map phi, we get that this should be nothing but alpha 1 phi E1 plus alpha 2 phi E2 plus dot, 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 alpha n phi En. But notice this can be written as, I already know that phi acting on E1 is this row vector, this column vector 1 1, A21, dot, 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 up to AM1, right? This is plus alpha 2. This I know to be A12, A22, so on up to AM2, and so on up to alpha n multiplying A1n, A2n, dot, 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 up to AMN. Now go back to that very old observation that we made at the very beginning of this course. This linear combination of columns can actually be written as A11, A12, so on up to A1n, A21, A22, up to A2n, AM1, AM2, AMN. This multiplying the column vector alpha 1, alpha 2 to alpha n. In other words, phi's action on the n tuple V is nothing but this matrix A into the n tuple V. Yeah, and this V is arbitrary. So that means this representation that I have of phi with in terms of this matrix A, this M cross N matrix A, this works out for every vector V. So this is not some works for some specific vectors V, it works for all. So therefore, this represents the matrix, the linear map phi completely. This A is a matrix representation of this linear operator, linear transformation phi. If I look back this representation A, what I notice is that this matrix A is nothing but, so listen carefully, This is nothing but the first column is phi acting on E1. The second column is phi acting on E2, and so on up to phi acting on En. So the columns are indeed the actions of the linear map phi on the various basis vectors. This into V. And this should not come as a surprise, because you see, what is this first column of A anyway? First column of A is in fact A multiplying E1, right? Second column is A multiplying E2, and so on, A multiplying En. So then what we have essentially found out is that when I have a linear map from Fn to Fm, then without loss of generality, I may assume that this is given by a matrix A, where the first, so listen carefully, but the first column of A is the action of the linear map on E1. The second column of A is the action of the linear map on the second basis vector E2, and so on. The final, the nth column is the action of the linear map on the nth standard basis vector En, right? So every linear map from F to the N to F to the M is represented by a matrix in Fm cross N. Yeah. Okay. Now, so I hope you do understand what's happening. Now, here is the question. What would happen if my vector space is an abstract vector space and not a vector space which is the collection of all n tuples or m tuples? We've already seen that matrices also do form vector spaces, functions form vector spaces, polynomials form vector spaces. There are all sorts of weird vector spaces all around us. And obviously, between those vector spaces also, there could be linear maps. How would those linear maps look like? So this observation characterizes all linear maps from the vector spaces which are tuples of numbers. Yeah. How do we characterize linear maps between vector spaces which are not tuples of numbers? So here's the question: how to visualize, or rather characterize, how to characterize linear maps between abstract vector spaces, of course, of finite dimensions. Right? Okay. The answer to this question will actually take us back to our infamous fifth lecture. Right? Remember the fifth lecture, the final module, we talked about coordinates. Right? Now, now what were coordinates? So let me remind you that suppose we have a vector space. So V is a vector space over a field F. Dimension of V is, say, n, which is finite. Okay, then one can set up a map like this. So let B, which is V1 dot 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 up to Vn, yeah, a subset of V, is an ordered was important, remember, ordered basis for V. yeah, as a vector space over F. Then we said that there is this identification. So given a vector V, an arbitrary vector V in V, I can identify V with VB, this was the notation, which is actually an element in F to the N. How did this representation, how did this identification work? How did we do this identification? Well, because V1 up to Vn is an ordered basis, is a basis to start with for V. I know that V can be represented uniquely by alpha 1 V1 plus dot 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 up to alpha n Vn, where these alpha i's are scalars. They are unique because it's a basis. From the ordered basis, VB, this is by definition the n tuple that we obtain by stacking the coefficients. So this is how the identification works. Start with a vector V, arbitrary from the vector space capital V, obtain the unique representation of this vector V as a linear combination, as a unique linear combination of the basis vectors, pick out those coefficients, stack them up into a column. That is your representation. So that is how the identification is done. What we are going to notice here is that this identification is in fact an isomorphism of two vector spaces. Yeah, indeed. So let me give this a name, this identification. This weird symbol is the symbol that denotes the identification. This is, we claim that it's a map from V to F to the N, right? What does it do? It takes a V and it maps it to its representation with the ordered basis B. Okay, we claim that this is an isomorphism. If you remember from the last lecture, isomorphism means that is, this is a linear map and this is bijective. So bijective would mean there is an inverse, and we have already seen that the inverse will also be a linear map. So therefore it's an invertible linear map, which means it's an isomorphism. Yeah, why is that so? So first we check that this is indeed linear. Very easy to do. Suppose I have two vectors V and V tilde. Two vectors are there in V. So V admits a representation alpha 1 V1 plus dot 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 up to alpha n Vn. V tilde admits a representation alpha 1 tilde V1 plus dot 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 up to alpha n tilde Vn. Okay. So this of course means that V's representation in this basis is alpha 1 dot 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 up to alpha n, and V tilde's representation is alpha 1 tilde up to alpha n tilde, right? Of course, if I now look at V plus V tilde, this representation, in fact, alpha, alpha can be a scalar. So alpha times V plus V tilde, if I look at this representation, this is going to be, so first I notice, this is, I need to find out. So first I need to notice that alpha V plus V tilde can actually be written as alpha times alpha 1 V1 plus dot 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 up to alpha n Vn plus alpha 1 tilde V1 plus dot 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 up to alpha n tilde Vn. If I look at this from the properties of vector spaces, abstract vector spaces, this is nothing but alpha, I just rearrange alpha 1 plus alpha 1 tilde into V1 plus dot 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 alpha n plus alpha n tilde Vn, right? This is the linear combination for this vector. So this means from the rule of this map, of representation, the representation of this in terms of this ordered basis would be, I just have to stack up the coefficients. What is the first coefficient? This one, which happens to be alpha alpha 1 plus alpha 1 tilde. Second coefficient, alpha alpha 2 tilde, although I have not written it, but I am sure you can guess this. This finally alpha alpha n plus alpha n tilde. Yeah, and from the rule of vector addition and scalar multiplication of tuples of numbers, I know that this is nothing but alpha multiplying alpha 1 dot 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 up to alpha n plus alpha 1 tilde dot 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 up to alpha n tilde, which of course is nothing but alpha v representation plus v tilde representation. So notice this is this. So this map, yeah, satisfies the linearity property. This means this map is linear. And why bijective? Of course, we have already seen. Yeah, it is one-to-one and onto. Right? Why is it onto? Of course, onto means for. So let us look at where this the range and I mean the domain and the codomain. V is the domain, codomain is f to the n. Take any n tuple in f to the n. Look at the corresponding linear combination with the basis vectors. That is the vector that gets mapped to this linear combination, the n tuple. So let's say a1 up to an in f to the n is arbitrary. Note that v defined as a1 v1 plus dot 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 up to an vn is such that v is a1 up to an. Yeah, so there is something in the vector space V which gets mapped to this n tuple by this representation map, this identification map. So it's onto, right? Because this n tuple was arbitrary. Yeah, this is onto. Why 1 to 1? When does a linear map become onto 1 to 1? When the kernel is 0. Yeah, of course. So suppose there is some vector which goes to the 0 n tuple. That means what is the representation of that vector? 0 times v1 plus 0 times v2 plus dot 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 up to 0 times vn. That's the 0 vector. So only 0 vector gets mapped to the linear map to the n tuple 0. Yeah. So the kernel of this map is the 0 vector. Therefore, it's 1 to 1. So this is onto. I have just said that why this is 1 to 1. You have to check it. I've said this verbally. Just go ahead and check. So this is 1 to 1 and onto. So it's a bijection. It's a bijection and it's a linear map. So it's an isomorphism. Okay. Now, with this understanding of the isomorphism, what we will see is we will see one way of doing this matrix representation of a linear map between two arbitrary abstract vector spaces over the same field, right? And then we will, so this, at this point we'll end this module, and in the second module we'll understand the same thing from a different point of view, a more elaborate understanding. Yeah, but this one, the one that we're going to see now, is more sophisticated and much easier, in fact, once you get used to these ideas. The one that we'll see in the second module will be a little more elaborate, yeah, but will be a little, what should I say, a little cumbersome. Okay, now see. Okay, yeah. So suppose I have V, I have W, yeah, and there is this map phi. There is an isomorphism from V to f to the n by this basis vector, by the basis B. This is the representation. Similarly, between W and F to the M, which is the dimension of W. So um, uh, V W vector space over the same field F, dim V is equal to N, which is infinity, less than infinity. Dim W is M, which is also less. So they're both finite dimensional. So of course, okay, this is the representation. Say, let me call this BV, and this is BW, right? Can there be a map here? If there is a map here, that will be represented by a matrix because it's Fn to Fm. We have already seen that maps between linear maps between such vector spaces of tuples of numbers is represented by a matrix, right? Yeah, understandable, no? Now you are going to tell me, how do I get this matrix? Go back, what we have done to get the matrix. Yeah, look at the effect of the linear map on the basis vector E1. That will be the first column. On the basis vector E2, that will be the second column. On the basis vector E3, that will be the third column, and so on up to the nth basis vector, standard basis vector. So here also you have to do exactly the same thing. We just need to find out what this map does to the vector E1, what this map does to the vector E2, what this map does, so on to the nth basis vector. Yeah, where do they get mapped to in this Fm? But now, notice what is happening. This is a commutative diagram, which means this A must represent this phi. So this A must be such that when A acts on E1, listen carefully, this is very important. When A acts on E1, it is the same as, that action must be the same as take E1 from here. The action of A on E1, that is the first column of A, must be the same as E1 gets identified here, gets mapped by this phi. Whatever vector I get, that must get identified with this guy. So this must be AE1. You're getting my point, no? So here is the deal. AE1 must be the same as BV, its inverse acting on E1, phi acting on this, and its representation in BW. Yeah, that is what AE1 should be. What I've written here is just a mathematical expression for this green lined argument that I just said. So if you don't understand what's happening, go back to that portion of the video where I explain it, where I'm explaining this green line. Okay. So assuming that you have understood, I further simplified this to phi. Notice, what is this inverse of BV, this map? What does this mean? This means I need to find out that vector whose representation under the basis is E1. Yeah. Now what is that? E1 is 1 and all zeros. Okay. So what vector gets represented by 1 and all zeros? Go back to the rule. That means it's the linear combination given by 1 and all zeros. Linear combination is 1 into V1 plus 0 into V2 and so on. So, the first basis vector represented by BV is E1. So that means this will be phi acting on, the inverse is V1, and its representation must be obtained from BW. So similarly, AE2 will be phi acting on V2 and its representation in BW, and so on up to AEN phi VN BW. That's it. So that's the matrix. So the matrix A would then be phi V. Let me write it. Phi, make phi act on the first basis vector in the ordered basis BV. Represent that, that's a vector in W, so represent that in the basis of W. Look at action of phi on the second basis vector, express phi V2 in the basis of W, and so on. This is the first column, this is the second column. Ultimately, we get the nth column, which happens to be this. That's your matrix representation. So then what does this mean? If I define A like this, then this means for an arbitrary vector V, say V here, this gets mapped to phi V here. Okay. Through this identification, this would mean if V gets mapped here and phi V gets mapped here, their representations must follow multiplication by A. So let me write this down as a phi V BW is nothing but A V B V. That's the golden rule. You think about this, this is where we close the first module. But before you go to the second module, you have to solve these companion problems. Immediate attention problem. I'm asking you here to represent the derivative map between polynomials of fixed degree, yeah, within the space of polynomials of fixed degree, degree less than or equal, not fixed, degree less than or equal to some number. Show, yeah, first you'll show that this is a linear map between Rnx and Rnx. Rnx means all polynomials of degree less than or equal to n. And then you're going to find out a representation of that matrix in terms of this basis. If you do this exercise, that will help you understand the method of obtaining these matrix representations of linear maps. The second one is a little more tricky. Here you have to represent a linear map given by this in terms of these basis vectors. You need a basis in the domain as well as in the codomain. So these are the basis vectors. Yeah, you do these two immediate representation problems, and then if you're confused as to what is happening, you have to see the second module, which explains in more detail why the matrix of the representation that we have obtained in the first module is correct. All right, so see you then.